Welcome to this first lecture today. Hi. My name is Alexei Preobrajenski. I work as a beamline lead, beamline scientist at one of the spectroscopic beamlines at Max IV, which is called FlexPES. And I will give you a brief introduction to X-ray photoelectron spectroscopy with specifically focused on the applications in synchrotron radiation. So what you cannot measure in the standard lab, but what you can measure at the synchrotron using XPS. So I will essentially speak about three things in XPS. This is the energy positions and what we can learn from the energy positions of the lines. I will speak about the shapes of the lines and what complications you can expect when you are looking on the XPS spectra in terms of line shapes. And also a little bit about the quantitative analysis of what we can learn from the intensities of the lines. So positions, shapes, intensities. And at the end, I will show you a few examples of how XPS can be used in different synchrotron experiments. So as I didn't really know how many of you are familiar with XPS and to what extent, the lecture is pretty superficial. So if you have more questions, then you can ask them later or in the coffee. But let's dive in. And first thing is I should recommend you good books on the topic. And the absolute hit here is the book by Stefan Hüfner, Photoelectron Spectroscopy. So if you want to learn photoelectron spectroscopy properly and use it in your everyday scientific analysis and instrumentation, then you should certainly read this book because it covers all aspects of photoelectron spectroscopy. Then this book, this is a very good introduction into just core level XPS in applications to synchrotron radiation. So if you want to apply it at synchrotron radiation instrumentation milieu, then you should probably read this book edited by Wolfgang Eberhard. And finally, this book is if you want to learn about more modern developments in photoelectron spectroscopy and specifically in angular resolved photoelectron spectroscopy. Now, the general principle of photoelectron spectroscopy is very simple. It's a photon in, electron out technique based on Einstein photoelectric effect, where you have an initial neutral state and core ionized final state plus one ejected electron, which kinetic energy you are measuring. And so if you promote this core electron outside of the system, above the vacuum level, you can measure its kinetic energy. And if you know exactly the photon energy you're applying, and the work function for the solids, then you can find out, and you measure the kinetic energy of the electron, then you find out what is the binding energy of the system before, in the ground state, before you excited the electron. So we should probably look a little bit on not only on the XPS, but also on the related techniques here in this context. And first, we should understand that for the core hole creation, there are two processes and two techniques which are in a way similar. In one process, we photoionize the system, so the electrons is going out of the system, and we can study it with the XPS, with X-ray photoemission spectroscopy. In another process, we don't ionize the system, we just core excite the system. And these processes can be studied with X-ray absorption spectroscopy. Then, once the core hole is created, there are secondary processes of core hole decay. And there are two of them. Auger electron emission, when the core hole is filled and Auger electron is flying out of the system. And there is an X-ray emission when there is this is a like photon out process. The core hole is filled and an excess of energy is going out as a X-ray emission photon. And for the sake of completion, we should also mention processes which are not touching the core hole, but they're relevant. And this is ultraviolet photoelectron spectroscopy, where we are directly probing the valence band states, and valence band states in case of solids, and also ultraviolet and visible absorption spectroscopy, where we don't ionize the system, but we just excite it here. And this is optical spectroscopy normally performed with lasers. If we speak about solids, then what we have in the electron levels of the solids, it is all reflected in the spectrum, in the photoemission spectrum. So if you have core levels here, and we have valence band here, they're reflected as peaks, photoemission peaks, and as a valence band region in the photoelectron spectrum. These are, I denoted them red, they are called primary electrons, plus also Auger electrons are also counted as primary electrons. On top of that, when electrons are transported towards a sample surface, they are getting scattered in inelastic processes, and this inelastic scattering creates a lot of secondary electrons, which is visible as a large tail, the background tail under the primary electrons here. So what about surface sensitivity of these electrons? The red, the primary electrons, they are normally very surface sensitive. So they can travel not very large distances, maybe 1 or 2 nanometers, maybe 3, and then the secondary electrons can travel some 5, 10 nanometers. And why is that? This is can be explained with this universal curve for inelastic mean free path of electrons in solids. Essentially, if the kinetic energy is relatively large, like for primary electrons, the electron can easily lose its energy and create some secondary electrons, so it may not reach the surface. While secondary electrons, they have very low energies, and simply they don't have enough energy to lose it on some scattering events. There are no scattering events with high cross sections which are available for the secondary electrons to lose their energy. That's why they can travel large distances without actually any scattering. And that's why the information depth from secondary electrons is larger than from the primary electrons. From the experimental setup, what we need is a pretty simple technique. We need a photon source. It can be an X-ray tube if you're interested in core levels, or it can be ultraviolet lamp or a laser if you're only interested in valence states. Or if you're interested in everything, then the best option is to use synchrotron. Then the photons are hitting the system. It is creating a lot of photoelectrons. These photoelectrons are going through the lens system, and they are focused on the entrance slit of the hemispheres. And in the hemispheres, they are deflected onto the detector. And as you can understand, this can happen only in high vacuum, because otherwise the electrons will hit some particles on the way, and they will just not reach the photoelectron analyzer. That's why the vacuum conditions for photoelectron spectroscopy are normally ultra high vacuum. So this is a precious better than 10 to minus 8 torr or millibar. And yeah, so what we are getting is something like this. These are typical spectra of metals where we have valence band region and some core levels visible here. Plus, we would have some Auger signals, which are not in this spectrum. So if you look more closely on what is happening inside the photoelectron analyzer, so the lens column is used for focusing the electrons on the slit, as I said, and then in the hemispheres between inner and outer hemisphere, the electrons are deflected differently, so they they have an energy dispersion on the detector. So this green path, for example, it depends on the path energy of the analyzer we select. So the path energy is the energy of this middle trajectory, so to say. So for example, one can say that the green trajectory is something like 100 electron volts, and red will be something like 95, and blue will be something like 105. And on the detector, the image will look like that. In the case of angle integrated spectroscopy, so when we are not interested in angle, we are just averaging over the angle, and we are getting this integrated signal, which is our XPS spectrum. In case of ARPES, we are also interested in the angular distribution of these electrons. And in case of ARPES, we are also using a different lens and different focusing system. So detector is in all cases a stack of multi-channel plates, which looks like that. And then there are two readout options. After the multi-channel plates, you either have a phosphorus screen and a CCD camera, and then you're recording frames in the camera with certain frequency. Or if you are interested in time-resolved experiments, then instead of phosphor and CCD, you can use a delay line detector, and then you are sensitive to individual events. In the multi-channel plate, this is essentially a photoelectron multiplier, so it's a silicon plate with channels cut in the silicon plate, and you apply high voltage across it, and for one incoming electron, it creates an avalanche of electrons on the way in each channel. So the amplification factor in each MCP can be about 10 to 3. So if you have a Z stack of 2 or 3 plates, you can amplify your signal by a factor of million or billion. The experimental setups which you can buy commercially, they normally always hemispherical photoelectron analyzer. In the early days, there were some also cylindrical analyzers, but nowadays it's essentially only the hemispherical analyzers. They're good for high resolution XPS and UPS, Auger electron spectroscopy, very good for ARPES measurements and X-ray photoelectron diffraction. These are standard. So these are less standard if you are interested in, for example, spin resolved measurements. Then you have to use a photoelectron analyzer with a specific detector. In this case, it's a mini-mode type detector. And then you can study magnetic properties of your system. Or you can use this kind of spectrometers with a lot of differential pumps on the way for ambient pressure XPS. If you are interested in real-time processes, in catalytic processes, you always use this AP-XPS technique. Also, you can find analyzers optimized for HAXPS, hard X-ray photoelectron spectroscopy. So they have electronics capable of handling electrons up to 10 and maybe even more than 10 kiloelectron volts. So the normal standard analyzer, they handle electrons up to 2000 electron volts, something like that. Then, on top of that, you may find photoelectron spectrometers which are not hemispherical. This is a very special case. They are time-of-flight analyzers. They are using full cone ARPES detection, for example, for ARPES. So they are slitless. They don't have an entrance slit. So you have a complete ARPES map on the detector. These analyzers have to use pulsed source, obviously, because they're relying on so the kinetic energy is calculated from the time of flight of electron. So you have to know the exact starting event of your excitation. That's why you are using pulse source, and you are synchronize it with the analyzer measurement process. So this photoelectron analyzers are used essentially at synchrotrons and for time resolved measurements mainly. Then, so if you think about photoelectron spectroscopy, what can we actually learn from photoelectron spectroscopy, or what processes do we study with photoelectron spectroscopy? So, first of all, of course, with photoelectron spectroscopy, we can look on chemical states, chemical shifts. We can identify different chemical species in your sample, and this is called core-level XPS, or electron spectroscopy for chemical analysis. This is the same ESCA. Then you can look on the valence states. This is called UPS, ultraviolet photoelectron spectroscopy. Then you can use on the secondary processes. So if you create a core hole, you can study how fast the core hole is decaying, for example, using resonant photoelectron spectroscopy or resonant Auger spectroscopy. Atomic structure. If you have some adsorbates on the surface, by using photoelectron diffraction, you can study how the specific molecules are oriented on your surface. Band structure in surface in solids. This is angular resolved photoelectron spectroscopy. ARPES is a very popular technique for studying complex processes in crystalline solids. Magnetic properties. If you have a spin polarizing detector, you can study magnetic properties of your sample. Photoelectron microscopy is a great tool combining surface chemical sensitivity with spatial resolution. So you can record the pictures of your sample with chemical sensitivity. So you can say, I want to have a picture only in, I don't know, carbon electrons or only in oxygen electrons and so on. You can also make movies of different processes with photoelectron microscopy. Finally, you can study electron dynamics by using time-resolved photoelectron spectroscopy. So it's a very powerful technique, but today we will concentrate on chemical states studied with XPS or ESCA. Now, this technique appeared some 80 years ago, maybe 70 years ago, and it was discovered here in Sweden, in Uppsala University, in the group of Professor Kai Zygmunt. So here is Kai Zygmunt with his co-workers. Here's Kai Zygmunt with his co-workers, and they are looking on the very first prototype of the photoelectron analyzer. So they started their work in late 50s, and the first book, famous book on ESCA, was published in the end of 60s, and Kai Zygmunt got a Nobel Prize for these developments in 1981. So, binding energies and chemical shifts. If we speak about binding energies, binding energy is essentially multi-electron property. So this is a difference in total energy between the ground system and the core excited system. That means it is not a one electron property, but this is a property of the whole system, including the relaxation of electrons after the creation of a core hole. And what we are interested in is normally not even the absolute binding energy, but rather the chemical shifts. So the difference in binding energy between different chemical species. This chemical shifts, this is, as I say, this is the main property we are interested in. And one can separate the chemical shifts into initial state effects and final state effects. So initial state effects are due to the static charge transfer in the ground state, and final state effects are due to the dynamic relaxation of electron clouds on the creation of a core hole. Now, no matter where electrons are shifted in the valence band in the initial state or as a result of the final state screening. The principle is more or less the same. So if you have in the valence states an excess of electron density, and then you kick off an electron from the core hole, then the kinetic energy of the measured electron becomes higher as compared to the neutral state. And if you have a lack of electrons, so electrons are dragged away from the system or a neighboring atom, for example, then the attraction with the core hole is larger, and the kinetic energy of the outgoing electron is smaller. So on the kinetic energy scale, these blue lines, those where we have an excess of electron density in the valence states, will have higher kinetic energy. On the binding energy scale, they will have lower binding energy. So this is a general principle. Let's look on some examples. This is the simplest possible example, lithium metal, a very simple metal. And if we compare the metal and a lithium oxide, what is the difference? In lithium metal, 2s electrons, those you can think of, these are 2s electrons, for example. So 2s electrons can do screen the core hole, and this results in smaller binding energy for the lithium metal. And in case of lithium oxide, the 2s electrons on lithium are no longer available for screening because they're gone to the oxygen atom and trying to fill the shell of the oxygen atom. And that's why what we have is larger binding energy for the lithium oxide. So this is resulting in this chemical shift. And this chemical shift is obviously due to the initial, essentially mainly due to the initial state effect, because already in the ground state, we have this shift of electrons from lithium to oxygen. So it's not a result of the core hole creation. It is already there. If you calculate the ground state properties, you will have it there. Of course, the absolute value of the shift is affected by the core hole and the relaxation, but the trends are mainly determined by the initial state effect in this case. Let's look on another example. This is so-called ESCA molecule. This is a 3-fluoroacetate, which they used in the early days to demonstrate the capabilities of the ESCA technique. This is an interesting molecule in that sense because it has 4 carbon atoms and all 4 are in different chemical surrounding. So one is surrounded by only hydrogen and 1 carbon. One has 1 oxygen neighbor. The third one has 2 oxygen neighbors. And the last one has 3 fluorine neighbors. And obviously, the electron density is distributed from the carbon atoms to its neighbors in this sequence from here to here to here and to here. So this one has least electrons available for core hole screening. And this is correlating more or less with the differences in pulling electronegativity in these bonds, which is understandable. And again, this is mainly the initial state effect because the clouds, the electron clouds are already distributed in the ground state like that. Of course, again, it is affected by the core hole. So the absolute shifts here, they cannot be calculated only in the ground state. This is another example. In this case, we have a nitrogen molecule adsorbed on a nickel metal. Nitrogen has a strong bond, and the interaction with the substrate is relatively weak. So if you measure the XPS spectra of nitrogen in this system, you will observe 2 peaks, and from the angle dependence, you can figure out which peak corresponds to which nitrogen atom in this system. And despite the fact that in the ground state, both nitrogen atoms are relatively close to each other, we have a very big chemical shift here, 1.3 eV. And this is a demonstration mainly of the final state effect, because in the final state relaxation, the electrons from the substrate can affect the core hole, or the other way around. The electrons surrounding the nitrogen, they can freely go into the surface for this atom, but not for that atom. That's why we have difference in the chemical state of these two atoms. So we have a difference in the XPS spectrum. So this is mainly the final state effect in this case. One can understand this big shift of 1.3 eV if we use so-called Z+1 approximation, where the core ionized atom nitrogen is replaced with an oxygen atom. Z+1 means so the charge is increased by 1 in this case. This is like emulating the existence of a core hole. And if you calculate the difference in absorption between this and this molecule, so the same molecule but absorbed differently, it is about 1.3 eV. Now, it was about the binding energies and chemical shifts, but so far we were talking only about singlets, S states. But if you are working with p orbitals, so d or f orbitals, you will always result not in one peak, but you will see doublet, and this doublet is a result of spin orbital coupling. And the intensity ratio between these doublets reflect the core level population, 1 to 2, 2 to 3, 3 to 4. And this property, the shift between these peaks is determined by this spin orbital coupling, and it is not affected by the chemical surrounding so much. So this is essentially the atomic property. Which is a great thing if you are fitting your spectrum, which contains either P or D or F states. You have to keep the separation always constant, because this allows you to get some sanity check of your fit. So this is in a way it is easier to fit spectra containing doublets than spectra containing singlets, because you have this additional constraint there. The ratio, intensity ratio, though, can change a little bit. This is a different story, but essentially they try to keep this ratio 1 to 2, 2 to 3, and 3 to 4. Now you understand that this is not a chemical shift. This is totally different thing. So this is the spin orbit splitting, the atomic property of a system. Has nothing to do with the bonding. So now the shape of each individual components, how is it? What is the shape of each individual components? First of all, it is defined by the intrinsic line width, which is determined by the finite lifetime of the core hole. And it is reflected in the Lorentzian shape like this. And the lifetime of the core hole, the larger the lifetime, obviously, the sharper is the peak, the smaller is gamma. And the shorter is the lifetime, then the broader is the peak. And the lifetime is determined by the decay processes. If the processes are very probable, then the line is very broad. For example, in 1s lines of carbon, nitrogen, oxygen, the typical life broadening, this gamma is 2 gamma is around 100 or 150 millielectron volts. So this is the intrinsic line width. But on top of that, it would be nice if all our lines would look like that. It would be very easy to fit them. In reality, though, we have many complications. So we may have so-called final state multiplets. We'll go later into that. we can have in molecules, we can have many body excitations like shake-up satellites and shake-off satellites. We can also have molecular vibrations, which are reflected in the shape of the lines. In solids, this is corresponding to the shake-up in solids corresponds to this broader peak, shake-up satellites, and also in asymmetry of the lines. And the vibrational broadening is reflected in the broadening of the lines due to the phonons. Plus, you can have extrinsic losses due to the scattering processes when electrons are scattered in the matter towards the surface. All this complicates our interpretation of the lines. Plus, on top of that, we have instrumental broadening, which is can broaden all of these shapes. So let's look first on the final state multiplets here. This is something which is typical for open shell systems when you have unpaired electrons in the valence band. A very simple and very prominent example here is oxygen molecule in gas phase. If you measure an XPS oxygen spectrum, you will see that it has two peaks instead of one. And these two peaks, this is the result of the unpaired spin of the non-zero spin. Spin is one in this molecule, and if we create a core hole, the spin of the core hole can couple differently to the this spin of the system, and it is resulting into two multiplet peaks due to exchange coupling. So if we now take instead of oxygen molecule, we will take water molecule. It also have oxygen atom, and we will record the spectrum from the water molecule. Will it have two peaks? No, it will have one peak, because in this case the shell is closed and the ground state spin is zero, so the system has nothing to couple to the core hole spin. And fortunately for us, when we interpret spectra of oxygen, for example, in different oxides, this is almost always the same, always the case that oxygen tends to become closed shell, so it attracts electrons in oxides. And if you measure a typical oxide spectrum, then you will see only one peak for one chemical species. Otherwise, it would be more complicated to interpret the data. But of course, this is not visible only in S states. It's more visible actually in 2p and 3d states. This is in solids, for example. This is manganese 2p XPS and manganese oxide. And this complex shape here, this is due to the same effect that when we create a core hole, the core hole can couple differently to the spins of electrons in the valence shell, creating a variety of different multiplet peaks. So, in principle, if you want to make a good peak fit of this, you have to calculate the multiplet structure and use several peaks for fitting just one chemical state. So it's a complication. It's even better visible here in chromium compounds. We have different chromium compounds here, where the electron configuration of chromium atom is changing from D0, no d electrons at all, to D3, 3d electrons. So, and we can see that in this case, if we don't have any d electrons in the core, in the valence shell, then our 2p core hole, this is 2p, chromium 2p spectra, has nothing to couple to, and it has only one single line here. But the more d electrons we create, the more open the shell becomes, the more complex the shape also becomes here. So this is final state multiplets. Now, next thing is satellites due to multiparticle interactions. This is here a neon spectrum and neon gas. What we see is a main line here due to the promotion of 1s electrons and measuring the kinetic energy of these electrons. And then we have a row of satellite lines. This is the same line essentially, but it has somewhat lower energy because we, in addition, lose some energy on exciting the valence electrons into the unoccupied valence states. And if we do the same, but we excite these electrons into the continuum above the vacuum level, then we have a continuum excitation here, which is called shake off, because the electron is going off the system. So here it stays in the system. So discrete shake-ups and continuous shake-offs. This is what is typical in the molecules. And this can be visible also in solids. This is very often one can see these shake-up satellites also in the solids. Now, if we work with metal systems, in addition to that, we can see that the lines can get asymmetric shapes. So the asymmetry can be described with this Daniak-Sunjic formula, where alpha is the asymmetry parameter. It's a parameter between 0 and 1. 0 is for totally symmetric shape, and 1 for very strongly asymmetric. So this is how it looks. If we we can see how it looks for different asymmetry parameters. Again, alpha 0 is the Lorentzian shape here. So it is converging to Lorentzian shape. And if gamma goes to 0, the lifetime broadening, then we are getting a singularity here. So for typical spectra of metals, the asymmetry parameter is something between 0.05 and 0.35. And for semiconductors, the symmetry parameter is close to 0. Why is that? Very simplified. One can explain it in the following picture. So whenever you have a gapless system, there is no energy gap here. You can excite extremely, so you can excite electrons from the from the Fermi age a little bit above with very small excitation. So in addition to this line, you will have this line, which is the same, but it is reduced in energy because we have to excite this particle in addition. And then the next one, because we have to excite this one, and the next one, and so on. And one can see also that this asymmetric tail goes down here because the probability of this excitation is smaller than the probability of that excitation. So this is a very natural shape actually for the gapless systems. So you cannot create a line which would not have any excitations in addition in metallic systems. That's why you always have an asymmetric shape. Then on top of that, we may have some vibrational effects in XPS. So this is a picture for molecules showing the initial potential energy curve and the final potential energy curve with the vibrational quantum states here, and the overlaps are showing the profiles of the wave functions for different vibrational quanta. And in the so-called southern core ionization, we always have the ionization process is faster than the process of deforming the molecule. And that's why our transitions in this case are always vertical. This is so-called Franck-Condon transitions. And the overlap integrals are reflecting the intensity of the resulting progression of the XPS peaks. So this is the blue one, the red one, the green, and the violet. So something like that. This is schematic, of course. And in the spectra, it may look like this. So if you have a methane molecule, you have a symmetrical stretching here. So you're creating the vibration. You have vibrational quanta corresponding to this stretching vibration, and then we can see excitations to different vibrational levels. If you have a more complex molecule, for example, ethane, where you have already two different normal modes of vibration, then the spectrum becomes more complex, of course. And that's understandable that if you go from a molecule to a solid, you cannot already resolve any individual vibrations. What you will see in a solid is rather a vibrational broadening. So this is shown here in the silicon 2p line. If you increase the temperature in the sample, you see the vibrational broadening, that the line becomes broader. So this is another complication in the shapes. And on top of that, as I said, we have instrumental broadening. And this is, first of all, the broadening resulting from the finite energy resolution of the monochromate and the analyzer. You cannot select, even if your instrument is super good and technically you can get perfect resolution, very, very, very thin lines, you still need some intensity. And this is always a balance between resolution and intensity in a real experiment. So you have to sacrifice your resolution for the sake of intensity. And that's why the resolution is always finite. So normally this instrumental broadening is represented by a Gaussian distribution. And that's why in the simplest possible form, the final final line shape is a convolution of the Lorentzian shape and the Gaussian shape, which is called the Voigt function shape. So, and many systems can be fitted with this Voigt functions, but of course, if your lines are asymmetric, then instead of the Lorentzian shape, you have to use this asymmetric Doniak-Sunjic shape in the peak fit analysis. All right, then we were talking now about only about primary electrons, but as I mentioned in the beginning, in the solids you also have secondary electrons, and they are creating a background under your primary electrons. So the shape of this secondary background is actually determined by the primary spectrum and by the loss function, so the probability of inelastic energy loss here. If the loss function can be approximated with a constant, then what we are getting is a so-called Shirley background. This is the Shirley background here. So essentially, this is an integral over the primary electrons only. So we are going over the primary electrons and we're integrating this intensity and we're getting this background. In some cases, it is also possible to fit the background with linear or polynomial background, like in this case, 3s. But normally people are using Shirley background. This is a standard procedure. Sometimes it is difficult to use only Shirley background. For example, here, the intensity of the lines as compared to the intensity's background is small. And if you use just the Shirley background, this is this B2. So first you start with a linear background, then you integrate, you are getting this Shirley background. But it doesn't look very physical because it doesn't fit your spectrum here at the same angle, so to say. then the people can use so-called iterative Shirley background. Then they use this B2 background, they subtract it, they do the integration again, they're getting B3 and then B4 and so on, until it converges to the iterative Shirley background. And if sometimes you always have to use two-guard background, this is more complex. This is there you have to use a special loss function. It can be either universal or it can be material specific. It's normally a parametric function, and it's pretty complicated. But here I show you just to get an impression, to give you an impression that the background may depend very strongly on how exactly your material is distributed in the matrix. So this is calculation where the copper atoms are distributed in the gold matrix differently. So it's the same amount of copper, the primary spectrum is the same, but due to the different scattering functions, you're getting different backgrounds here. All right. Also, what can be learned from XPS is the quantitative analysis. And this is what we're interested in. We are interested in atomic concentrations of elements. And for calculating the atomic concentrations, we need to calculate first or measure first the peak area of a specific peak. And then also we have to have so-called relative sensitivity factors, which are affecting the intensities. And these are these include the photoionization cross section, and we have to take into account the inelastic mean-free path, and also the transmission function of the analyzer, which is kinetic energy dependent. And in the case of synchrotron, where you have a source with variable photon energy, you have to use the photon flux intensity also in this sensitivity factor. But if you, in practice though, at least at synchrotron, people try to use the same kinetic energy, so at least they have the same inelastic mean-free path and the same analyzer transmission function for comparison. So they try to adjust the photon energy in such a way that the kinetic energy of the two lines, you want to compare two lines, and the intensity of those. So you try to make them measured with the same kinetic energy. Then it's much easier because then you only have to look into the photoionization cross sections and the intensity flux of which you're using for these two. You cannot do this with a laboratory source, but with the synchrotron, you can always adjust the photon energy and therefore adjust the kinetic energy of the outgoing electron. So why would we use synchrotron, and what are the advantages of using synchrotron in the context of XPS? First of all, we have variable photon energy from several electron volts to several tens of hundreds electron volts, and this allows us to vary the surface sensitivity. Then we have normally at synchrotron we can have very good energy resolution. We can have very high flux. We can vary the focus size. So sometimes for some samples we need very small focus, like maybe a few microns. For some samples you are not interested in a small focus. On the contrary, you want to have very large spot on the sample. For example, your sample is very sensitive to the radiation damage, and then you don't want large small spot, you want large spot. So this is all adjustable at the synchrotron normally with our standard instrumentation. Plus, at synchrotron you can also enjoy the possibility of variable photon polarization. So you can polarize the beams so that the E vector is either horizontal, linear horizontal or linear vertical, or it is circular, or it is elliptical, or it is inclined, linear but inclined. So all these options are available with the standard undulators at the synchrotron. Of course, there are cons in using synchrotron, and essentially this is a need to think ahead. You cannot go to the lab and do experiment tomorrow. If you have a good idea, you have to submit a proposal, and then this proposal has to be evaluated. So it is several months between the idea comes in your head and a possibility to perform an experiment. And of course, you also need more manpower and extra costs to enable these synchrotron measurements. At MAX 4, we have several beamlines, 7, which can perform photoelectron studies. 5 of them are located on the small ring. Actually, all beamlines on the small ring can perform photoelectron studies of different kind. And also 2 beamlines on the large ring dedicated to soft X-rays. They also can perform photoelectron studies, Veritas and Hippie. Plus, there is one beamline for ARPES, hard X-ray photoelectron spectroscopy, which is in planning. Yes, so let's look on some examples now. How we can extract chemical and structural information from the spectra. This is an example, very simple example, where you have clean surfaces of nickel aluminum, 2 different surfaces, and you are measuring the aluminum spectra from these surfaces with a photon energy of 155 eV. You can adjust the photon energy, as I said. And this is a typical surface chemical shift, which you may expect in these lines. So this peak, the blue peak, corresponds to the atoms lying on the very surface, and the red peak corresponds to the bulk atoms. Same here. And the surface sensitivity is extremely high in this case, because we are selecting the photon energy in such a way that our kinetic energy is the most surface sensitive. It's lying here. So the information depth, one can say, is around 0.4 nanometers. So we are sensitive to only maybe 2-3 atomic layers in this case. If you would do the same experiment with aluminum K alpha in a standard laboratory, you would have this inelastic mean-free path around 2 nanometers. So you will be sensing several more monolayers, and the contribution from the surface will be much, much smaller. So this blue peak will be almost not visible, plus the resolution will be much worse. So instead of this nice resolved peaks, you will see one large peak. Another example, this is how we can follow surface reactions with the synchrotron radiation. This is an example here of a surface reaction. We have this molecule, DBBA. It has 2 bromine atoms. And if you absorb it on a surface, for example, on gold, we can, at certain temperature, we can crack the bromine bonds and create these chains. And if we keep heating it, we can even create these ribbons. These are nanoribbons, carbon nanoribbons, or graphene nanoribbons. So this is how the spectrum may look like on different substrates. You see, this is the bromium 3D doublet. So this doublet corresponds to 1 chemical species. So on gold, if we deposit at room temperature, the molecules are intact, the bromine atoms are still sitting there, and we have only one doublet corresponding to these atoms. If you do the same on silver, though, at room temperature, the same molecule is touching the silver. Silver is more active, and then this bromine carbon bond can get cracked, and immediately the molecule stands upright, so that the second bond is protected from cracking, and that's why you start seeing 2 doublets corresponding to 2 different bromines. One is loose bromine on the surface, and one is still on the molecule. And if you do this on even more active copper surface, then due to the strong interaction with the copper and vibrations, temperature, you immediately lose both atoms and they become loose. So, and this you can, for example, for the case of silver here, you can do it like a temperature map. You can ramp the temperature from, in this case, some minus 80 degrees C, where you see the intact spectrum from intact molecule. And then when the temperature is increasing, you start to lose one species and you start to create another species. And then the other species is fully developed at certain temperature. So this is very simple example, but it is illustrating the possibility of doing surface reactions and measuring them live. And for this, obviously, you need very good surface sensitivity, because you have very small amount of, for example, these bromine atoms, and you have to be really surface sensitive to record them with a good resolution. Here is another example. This is more towards catalysis. This is rhodium surface, and this is stepwise oxidation of a rhodium surface. So we start with this rhodium 3D spectrum here. On the clean rhodium, it has two components, a bulk and a surface component. This is what we already have seen. If now we add a little bit of oxygen, a quarter of a monolayer of oxygen, the spectrum changes drastically, as you can see. And this is this blue component. This is essentially the same as the surface component, and it corresponds to the rhodium atoms which are not having any oxygen neighbors at all. So this is the same binding energy as before. In addition, now we are getting these green atoms, which and this green component, they are corresponding to the rhodium atoms which are in contact with one oxygen atom each. And that's why the binding energy is shifted to higher binding energies. If we add more, so we create a structure which is corresponding to half a monolayer of oxygen. Now we don't have any surface component anymore, because all atoms on the surface are touching one or two oxygen atoms. That's why this component is gone here, but instead we have a component corresponding to this green still. And in addition, we have a component corresponding to these orange atoms. This is atoms which have two oxygen neighbors, and that's why the component is shifted even further to the higher binding energies. Of course, you still have the bulk component here always. And so on. So if you continue oxidizing, you can create surroundings where rhodium atoms are surrounded by three oxygen atoms. This is this pink component. And then finally, you can create even surface oxide at certain conditions, where we can have now previously we always had only one oxygen component, because oxygen atoms have the same chemical environment more or less, but in here they have different chemical environment. This squeezed layer and this top layer, they have different chemical environment, and then we start seeing two peaks in the oxygen. So this is showing us how sensitive the technique is to very small changes in the surface composition and chemistry. Okay, another example here. This is graphene. You may know about graphene. This is a monolayer of carbon atoms in honeycomb structure. And this is graphene adsorbed on different, a monolayer adsorbed on different metallic substrates, and we are looking on carbon 1s line. So this is just the bulk HOPG, highly ranged pyrolytic graphite. This is monolayer on platinum, monolayer on iridium, monolayer on rhodium, on ruthenium, and a monolayer on nickel. And this is the picture showing what we see here and why we see different chemical components. So on these systems like rhodium and ruthenium, the interaction is strong the lattices are mismatched, what we see is a gradual corrugation of the graphene film, so that it's like a blanket. It's going down at certain absorption sites where the absorption is more preferable, and then it's going up again. And these areas corresponding to the pores and areas corresponding to the wires are clearly visible in the XPS, so that we can study it with XPS. And one can see that on nickel, for example, where the interaction is strong and the system is lattice matched, we only have only one component corresponding to strong interaction. What else? Sometimes we can learn many things also just by looking on the line shapes in the experiment. Here's another example. This is not graphene. This is a monolayer of boron nitride, where each boron is surrounded by 3 nitrogens, and each nitrogen is surrounded by 3 borons. So if you grow a monolayer of this material on nickel, 111, which is lattice matched, we don't create any corrugation. And we are looking on the boron spectra. We see that the boron core level has a metallic shape, although the material itself is a dead insulator, so it has a band gap of some 6 EV. But once it is in contact with the metal, the line shape becomes actually metallic in shape. If you start to grow more material on top, which is already no longer in contact with the metal, we start to develop a second component, which has this typical semiconductor shape. And this can be explained in terms of screening, the strong screening in the case of just one monolayer. So the electrons from the nickel substrate can screen the core hole and they create this metallic shape. And in case of a poor screening from the second and more layers, we don't see that, and we are resulting in purely symmetric semiconductor shape of the core line. So just by looking on the shape, sometimes you can say what is going on in your system. Okay, I think I will go to a summary. So XPS as a technique is very good for studying surface composition. So you can study both atomically clean surfaces, and you can study industry relevant surfaces as long as they are not very dirty and not very charging. You can study on-surface reactions, catalytic processes, absorption, desorption of atoms and molecules. It's also very good for studying sandwiches of different materials with very thin films. You can study organic layers, different organic molecules. And it's also very good for studying 2-dimensional, 1-dimensional, and layered materials. So everything which has relevance to the surface can be studied with XPS. For that, you need obviously monochromatic X-ray source, you need a photoelectron energy analyzer, you need good vacuum normally, and you need a relatively conductive sample. Also, as I said, the sample should not be very dirty, or you should have means for cleaning sample in vacuum somehow, either by heating or by ion sputtering, or else how. Maybe cleaving. Sometimes cleaving is a very popular method. Yes, and so what do we learn from this spectrum? We learn 3 things. We find out information about the binding energies, which gives us information about chemical states of photoionized species. Then line shapes gives us information about core hole lifetime, metallicity of the systems, potentially vibrations, multi-state, final state multiplets, etc. And of course, intensities can be used for finding out what is the composition of the surface. And finally, why we are using synchrotron? Because of extra surface sensitivity and possibility of doing depth profiling. So we can change the photon energy, and then we are looking differently deep into the sample. And also because we have very good energy resolution, higher flux, and smaller spot than what you have in a standard lab setup. Okay, I think that's my last slide. So we have time for questions. You're welcome to ask this.
Is the depth of the depth profile that is possible in the synchrotron?
Okay,
Here's the question.
I can repeat it. Yeah. So what is the information depth which you can with this technique get at synchrotron? So first of all, when the photons are hitting the sample, they are getting absorbed in a distance from the surface, maybe several hundred nanometers. So if you would use a photon in, photon out technique, then your information depth would be several hundred nanometers or even microns maybe. But since we are using this photon in, electron out technique, electrons, they cannot travel very long distances. They immediately lose their energy because of these secondary scattering processes. And that's why the typical information depth for primary electrons is, yeah, between half a nanometer and maybe 2-3 nanometers. So for secondary electrons, it's a little bit larger. That means that the technique is really sensitive to the surface. You cannot bring any sample from the pocket and start studying it because most likely your surface will be contaminated. So what you will see is first of all the contaminations. That's why it's not good for everything, but also it doesn't mean that the standard samples cannot be studied. We have many cases where companies are interested in studying certain surface compositions of, I don't know, steels or some other compounds on certain surfaces. And then it's just that the sample should not be very dirty. And then if you want, we can use high photon energy. Okay, we will look through the dirt into the sample, and it will be still possible to measure XPS. But in each case, it should be, it's a matter of trying. So if you have an idea of something can be measured with this technique, the good thing is to submit a fast access proposal because it normally doesn't need any long evaluation. And most likely you will get a few hours of beam just to test your idea and to test your sample. This is available at all beamlines doing photoelectron spectroscopy. Yes?
To calibrate the energy, we use the carbon. And we need some correction with energy.
You use carbon. Why?
To calibrate the energy.
How to calibrate the energy? The easiest way is, if your monochromator would be perfect, so what you type in the computer would correspond to reality 100%, then you would have the perfectly well-defined photon energy. And then if your analyzer is measuring kinetic energies also exactly, then it will give you the exact kinetic energy. So then you would need no energy calibration at all. But in reality, of course, there are these misalignments in the experimental setup, and in practice, you always, if you care about small shifts in your spectra, for each spectrum you have to do some certain energy calibration. For example, what we are using, like if you have a sample which has no internal Fermi H or no internal strong metallic line, then we can mount close to it, we can mount another sample, for example, a gold foil. And then after measuring your spectrum from your sample, we just shift to this reference sample, and then without changing anything on the setup, we're measuring with the same photon energy and same settings of the analyzer, we are measuring a spectrum from this reference. And then we know exactly what is the kinetic energy, what is the photon energy.
I think we will discuss it more in practical session of XPS and MS.
Yes. Also, if you want to know the photon energy exactly, there is a nice way. At synchrotron, you can measure a core level on the kinetic energy scale in the first order light. Each monochromator is transmitting not only the first order light, but also the second order light because of some imperfections. And this is a parasitic light. Normally, we don't want to have it, the second order light. But it has a good thing, because then if you record the same line on the kinetic energy scale with the first order line, and then, for example, you have excitation of 200 electron volts, and you measure kinetic energy 10 electron volts. Then if you measure at the kinetic energy of 10 plus 200, you will see a weak line also due to the second order light in your beam. And if you take the difference in energy between the first order light and the second order light, it gives you exactly the photon energy. So this is very, very solid way of finding the exact photon energy in the system.
Back row?
Maybe you.
What is the cooling and the heating mechanism that was shown in that picture? There was like a very nice temporal temperature versus the cooling and heating system there.
Okay. You are referring to this. Well, there are different cooling and heating systems. For example, Alexander recently installed a very fancy system with a laser. So there is a laser heating the back of the sample. We are at this beamline, we are not that sophisticated. We are using filament heating, plus we can apply high voltage so that, but this is no issue. We have a cryostat, a helium cryostat, so we can cool the sample down to helium temperatures. And then if you want to ramp the temperature stepwise, we just apply heating of the filament behind the sample. And we have a thermocouple attached to the sample so that we have a feedback, and we can create a linear ramp, for example. Then we are measuring spectra as a function of temperature.
Yeah. Back row, yeah, that's it.
I think it might be silly, but it's a bit basic question. I was thinking about the spin orbit coupling as a fingerprint of the elements. And I was thinking if we could tune that shift by applying some external magnetic field. So would be easier to basically stretch that thing. So when we do have lots of elements present, it would be a bit easier to. It's sort of like Zeeman effect in people trees.
I think the effect on the core levels will be not very big, or unless you have to apply huge magnetic fields. Then the problem with magnetic fields is anyway that you cannot measure the XPS at all, because you are in the magnetic field, the electrons will be spiraling away from the analyzer. So essentially, XPS is always relying on the fact that we have no magnetic fields in the area above the sample. So that's why people are even trying to use special anti-magnetic metals for screening the internal part of the vacuum vessels from any Earth magnetic fields or whatever magnetic fields. So maybe it's a good idea, but it's difficult to detect. Anyway.
Just for fun, so the other synchrotron, we had a big magnet, like 10 Tesla next to us when we measure the emissions. So when it switched polarity, so we also see it shifts spectrum, but it was like 5 meters away. So still definitely not the best. More question? Yes.
Okay, so for the deconvolution, you have shown there is a possibilities of the percentage of Lagrangian and Gaussian. So is there any maximum room for deconvoluting a particular thing? How percentage of the Gaussian and how much percentage Lagrangian should be, or depend on the different system?
What I would do, I would try to find in the literature some similar systems and maybe something to understand what the Lorentzian width would be approximately for the system, because this is the first and basic, it's very fundamental property of the this specific pole level, right, in a specific system. So as I mentioned here, for example, if we are speaking about simple molecules and we are measuring oxygen, carbon, nitrogen, 1s lines, then the Lorentzian widths are known. They are between 100 and 150 millielectron volts. So you would fix this as a parameter in your fit procedure. You would not allow it to go to 300 or to 1, right? So you will always try to fix the internal intrinsic width to a certain reasonable value. The Gaussian broadening, the instrumental broadening, is more relaxed in a way because I only talked about the instrumental broadening, but in principle it can also include different scattering and randomization processes in the sample. For example, the surface can be rough or something like that, and because of that the line can get broader, and this also can be included in the Gaussian. So Gaussian is probably less strict than the Lorentzian, I would say. So I would start always with finding out what is the expected internal broadening of my spectrum is. But there is no like an algorithm. Do this, and you will get a good fit. Fitting is a special. It deserves a lecture on itself.
That's why we have special class for fitting.